Now, this is a grounding note. This is just a general grounding note. It doesn't have to look exactly like what it is that we're going to do. Sometimes there's a sub panel here. I just like to keep everything the same except for this. I do like to show that there's 2 PV arrays, 2 strings of 14. This is just making sure we have that grounding in there. The city requires it. It is big on it for safety. Now we move over to the system values, all the voltages for the panels, the voltages and amperages required from the inverter data sheet. This is just so the numbers are all in one place so we can do our calculations down here. So let's verify. We have to get our panel data sheet out. These are 300 watt panels. So let's change this to 300 watt. There's 28 of them. Our voltage is 39.5 volts. Nominally, the voltage running through those lines is 32 volts. So that's the VMP, 32.0. And then similar to voltage potential, we have the current running through those lines. The maximum short circuit current is 10 amps. I'm sorry, the ISC, 10 amps. And the nominal current that's normally going through those lines is 9.42 amps. We already saw on our inverter the max voltage allowable for our inverter is 600 volts. And our max voltage, this is the PPT, is each one of these, this inverter has ports. So our electrical lines will go into the inverter, and the inverter will have ports here. They'll have 2 ports, sometimes 3 ports if you have 3 strings. You'll have different ports that you plug the electrical into on the direct current side, and then it will kick out the alternating current that you can use in your home on the alternating current side, the output. So per port, this is the range to turn the power on for the inverter. To turn the power on, this MPPT, this is the voltage range right here, 345 to 480 volts. The inverter turns on when the electrical panels get up to 345 volts, and then the inverter turns off if the power goes above 480 volts going in. Actually, this is a normal working range. It will turn off if it goes above 600 volts, I believe. So there's a safety factor there. But they just like to report it here. The average high temperature and the record low temperature, this you can get from weather data. It does matter. So say you're in Denver, Colorado, and it just snowed out. It's very cold, yet you have very hot sun shining down. It's a clear day. The voltages will surge. Okay, that's the most efficient you can have the panel. We want the panels cool, and we want a very sunny day. So the voltages will surge in these panels. And so, but if you're typically in a cloudy day, warmer temperatures, like maybe in Florida, the voltages will be nominal or operate normal or on the lower end. So it does matter. They just like to have the weather data, average high temperature for the region and record low temperature for the region. You can get that from weather data. Okay, this is where we start getting into per string, reporting our per string and doing some voltage calculations. Modules per string, we have 14 panels per string. We have 2 strings. Number of strings, 2 strings. Now, this is the branch or string voltage, the maximum voltage. And so we need the maximum voltage of the panels from the data sheet, 3.95 multiplied by how many panels are in that string. So 39.5, I'm sorry, 39.5 times 14. 553 volts. Okay? And then our nominal voltage running through those lines is 32 volts multiplied by 14. Let's change that. 32 volts times 14 panels. Let's see. Let's try that again. 32 times 14. 448 I think I saw. We need to get it. I'm going to do it on my calculator that I have here. 32 times 14. 448. 448 volts. Branch ISC, this is a maximum current going through those lines. Now, again, electrical class 101. The current in a string in series stays the same, but the current, when you put it in parallel, adds up. They multiply. The voltage in a series adds up, but the voltage in parallel stays the same. So they're opposite, voltage and amperage. So amperage, you need to multiply the number of strings multiplied by the module ISC, the maximum voltage. So that's 10.0 times 2 strings, so that's 20. Got 20 amps there. Do specific numbers. And then overall system amperage. This is the output, maximum output of the inverter. The maximum output of the inverter is 33.4 amps. 33.4 amps. Maximum output. Okay, so that information is all changed. Now we have down here some calculations. So we have 300 watt panels multiplied by 14 panels. We're kind of duplicating a lot of these calculations here. They just want to see the full system size in direct current. Let's see here. 300 times 14, 4,200 watts. This is basically Ohm's law from your electrical class 101. Power equals volts. P equals IV, volts times amps. Power equals amps, I, current, and times volts. That's the maximum power. So we have power. We can solve for amps. So our voltage, we said, was 553. 14, 553. And it's less than our 600 volts going into the inverter. So this complies. And we need to change our voltage here to, what was our voltage? 39.5. Okay? So we use Ohm's law to solve for amps in that line, 4,200. Divide by 553. And then the city makes you multiply by a safety factor, 1.25, 125%. So that number is 4,200 divided by 553 multiplied by 1.25 is 9.49 amps. 9.49 amps multiplied by 2 strings. The amperages multiply in parallel. So the maximum load you have going into that inverter is 9.49 times 2. That's with the safety factor, 18.98. 18.98 amps going into this inverter here. That's with the safety factor. And we already said we're allowed up to 24.1 amps per string. So I like to indicate here that we have 18.98 amps going in, and the load to the inverter, it's less than the load to the inverter, which is the 24.1. So our system complies there. We just want to show the city that the system complies. And this is input. The max output of the inverter on the alternating current side is 33. maximum output of the inverter is 33.4, multiplied by that safety factor 125% is 41.75. We already did this calculation, but a lot of this is repetitive just to verify and make sure that the system complies and all the electrical information is there. Now we have the total system amperage and the amount of current going through each line. Now we can figure out the wire size. First of all, we figured out the breaker size, 45 amps. So we can actually turn that white. And we have 45 amps, so we cannot use a 60 amp AC utility disconnect. The next highest one on the market is a 60 amp AC utility disconnect, most available at Home Depot. So we will use a 60 amp AC disconnect switch, and we will also indicate that here. Okay. Now that we have that determined, now all we need to determine is the wire size. What wire size do we need? Well, for number 10 wire, we do have a wire size. I do have a wire size chart in here, wire sizes in each project folder. I like to have that wire size chart there. It shows the gauge of the wire, number 10 gauge wire. If we're using the 90-degree rated wire, 90 degrees Celsius rated wire, we're allowed to have up to 40 amps in that line. However, so we see here 40 amps going through that number 10 line if we're using 90-degree rated wire. National Electric Code states for safety factors you need to derate that 40 amps by 80%. So that figure is 32 amps. So we're actually only allowed to have 32 amps going through that line for safety. Now number 10 wire, we can use number 10 wire here because we only have 18.98 amps going through that line. We want to indicate that here, 18.98 amps. We only have 18.98 amps maximum going all the way into this inverter. Okay, we've already figured that out. Now going out, we have more than 18 amps. We have 41.75 amps going through that line, which is over our 32 amps allowable. So we need to change the gauge of the wire from 10 gauge. Maybe we can go to 8 gauge wire. It's typically 10 gauge wire and then 8 gauge wire and then 6 gauge wire and 4 gauge wire, 2 gauge wire. Those are the ones that are on the market. 10, 8, 6, 4, 2. This is what they can just go walk into Home Depot and buy off the shelf. So, or any other electrical contractor. So let's try a number 8 gauge wire. In number 8 gauge wire, we're allowed 55 amps going through number 8 wire. So let's check 55 amps. Let's change this to number 8 gauge wire at 90-degree rating. We're allowed 55 amps going through those lines. However, the safety factor, 55 times 80%, it's 44 amps we're allowed going through those lines. Now we have 41.75 amps going through those lines, which is under this 44. So we are allowed to use number 8 wire going from in these lines all the way to the main service panel, from the inverter all the way to the main service panel. That needs to be number 8 gauge wire. And so we have 41.75 amps going through that line. We can indicate that here, 41.75 amps. It shows that we are under what is allowable in that line and the system complies. So let's change our wire gauges in these labels. Now, and let's also verify the quantities. First we have the quantity of wires. We have one positive wire for this string, one positive wire for this string. So that's 2 positive wires. We're using USE 2 type wire. This is for photovoltaic. This is for the direct current side. Once we get to the junction box. After the junction box, we can use THWN-2 type wire. Okay, so and then for the negative side, we have two negative. We have one negative wire for this string, one negative wire for this string, so we have two negative wires there. And those are both number 10. And the ground on the roof, there will be two grounds on the roof, one per string. And that is a higher gauge wire, so that if lightning happens or any electrical surge, the electricity will go through this wire because it's thicker. That number 8 gauge wire is thicker. It's the path of least resistance, and it will, so the electrical surge will go through this wire and save our solar panels. And this can be put in 3/4 inch conduit, so there are two conduits holding these wires in on the roof. We can now change that to white, actually by block. If you change it to white, you will not be able to see it when you make the PDF. So we want to change it by block. Okay, so now it goes, the electrical goes into this junction box, and from the junction box on the roof all the way to the inverter, we can use THWN wire. And let's just verify. We also have two positives, two negatives, two grounds, and two conduits. We're just changing the wire type there. We're not changing anything else. So each of those two wire bundles gets connected to this inverter in two separate ports, and this is direct current going through those lines from the panels, and it gets just transferred in this inverter. The function of this inverter is to change that electricity into the type of electricity you can use in your house, 240 volt alternating current electricity. It gets kicked out at 33.4 amps, and actually with the safety factor we were at 41.7. And remember, we can use number 8 wire, and this is still THWN type wire. There on alternating current, it's not positive and negative. The positive and negative is continuously changing. This is also electrical class 101. So it's continuously changing instantaneously from positive to negative. Both wires are. So you have one, and this is only one wire bundle coming from the inverter. So it transfers from two wire bundles going into the inverter with two ports and one wire bundle coming out. So for alternating current, you have an L1 line. The electrical transfers between L1 and L2 lines. So you have two of those lines plus a neutral line. So you have three wires, L1, L2, and neutral, carrying the electricity. And then you have one ground wire just in case of emergency or lightning or an electrical surge. The electrical goes through that ground wire straight to the ground. That's the path of least resistance. And so we do not need to make that larger. The city just requires number 8 typically. The National Electric Code, it requires number 8 ground wire. And this can all fit in 3/4 inch conduit. This is the tube that holds the wire. So that's a 3/4 inch diameter conduit. We can make that by block. Copy that, because this is going to be the same type of wire right here, going from the alternate. Oh, did it snap? Oh, it snapped over here. I'm going to move it. You have to watch out where it snaps to. See, that's why I don't like to have the snap on when I do these labels. Okay, so from the AC disconnect switch going to the main service panel, we have the same type of wire. Okay, this is almost complete. We just need to duplicate these numbers right here so we know our operating current, maximum operating current is 41.75, right? And our current coming off of that, the system current coming off of that inverter is 33.4 amps. nominal. So 33.4 amps nominal without the safety factor. And then our maximum voltage going through those lines, we showed up here. I can even copy these, Control C, and I paste them over here so I can copy them properly. 553 volts, and our operating voltage is 448 volts. Okay, these are all by block, and we are complete with this page. Save. I just showed you how to do all the electrical calculations, and I was going to put it off into a different lesson, but it works well here. It's better if I teach you this straight through, I think. So those are the electrical calculations, and I also taught you the structural calculations. So we'll save that. We've already copied the information. We can now turn this into a PDF. Export PDF 17 by 11. Since we're complete with this page, we're 100% complete with this page. And we can close that, save changes yes. And you can see our first PDF that's 100% complete is that electrical page. Okay? Now we go back and we go to page 4. I just showed you how to set up page 1, page 2, page 3. All that we have left to do on page 1 is to draft the project and to insert the drawing into here and then place the labels properly. Same thing with page 2. We need to draw the structural with rafters and everything, the structural detail, put it into our layout, and then insert it into this page and place the labels properly, and then that will be 100% complete. But now let's go on and do all the data sheets. I do the data sheets really fast. So module data sheet, this is still pulling the old data sheet out, so we'll delete that. We'll delete the old customer information. Control V, placing the new customer information. I do not have my snap on, so I like to have it on for this. Place it there. Ready to receive our data sheet. This is our first JPEG. This is where I turn my snap off, actually, because I don't like it snapping to anything. Page 1, let's insert page 2 of our data sheet. Page 2. Save. It says module data sheet there, module data sheet here. Everything is correct on this page. Save. And this page is 100% complete. We can create a PDF out of it. 17 by 11. Close. On to the inverter data sheet. This is still pulling the old inverter out. So we need to delete that. And we need to delete the old customer information. Control V, paste the new customer information. Snap right to that point. Turn my snap off because I'm going to be placing insert inverter data sheet. Page 1. Yes, that's the JPEG that I want to place. Insert page 2. Page 2. This is all in our project folder. Yes, that's the sheet I want to place in there. And now this page is 100% complete. I save it, export PDF, 17 by 11, and this page is complete. Close, yes, save. Now we move on to attachment data sheet. Our attachment data sheet is the same. It's still pulling these JPEGs from our folder, and that JPEG did not change, so it's still pulling those same JPEGs. This is correct. So all we need to do on this data sheet is delete old customer information, place the new customer information, snap, save, export PDF. Good. Next data sheet, the last data sheet is the rail data sheet. So this is the correct rail, so it's still pulling the same JPEG. This is just one JPEG for this data sheet. Some rails require 2 data sheets. But we will not be changing that, so let's just change the customer information. Delete. Control V is paste. Snap it to that point. Save. File, export, PDF. 17 by 11. And it's created that PDF. On to the warning placards. Last sheet is the warning placards. Okay. Now this sheet, these are all warning labels. So let's change the customer information first. This is something we've gotten good at and we know how to do. Control V. It's a new customer information. I save this. Now these are just warning placards. Junction box. So warning labels that go in the junction box. This is a DC disconnect. If we have a DC disconnect. Okay, right here, this is required by National Electric Code to have this warning label. It shows voltages and amperages of our system. So we need to change this. So we have 28 panels. This is exactly what is in that box on the electrical diagram. So we can transfer those numbers over. So 300 times 28 is 8,400 watts. And we're at 45 amps is the breaker size at 240 volts. We can pull up see all the data sheets that we've created so far? I like to pull up the single line diagram, this electrical diagram, and we can see, we can zoom in to this box, control and zoom in. I like to have it right there and we can transfer the numbers over exactly in order. 33.4 amps nominally, operating current, 448 volts nominal, 553 volts, and 41.75 amps maximum system current. Okay, so we've changed that. Then we go over here. This is the warning labels we have on our inverter. Nothing changes on those. Production meter, if we have a production meter. This one changes. Rated AC output current. We have a 45 amp breaker. So I like to change that. Main service panel warning labels that go on the main service panel. This is near the PV breaker on the panel cover. Again, we have a 45 amp photovoltaic breaker there. And this placard is special. It shows the map of the property and it shows where all of the electrical equipment is for the fire. Since this is specific to our project, it will change. So we will draft the project first. We'll draft the home first. And we're going to delete the old project. We're going to draft the home first, and then we will place in this file. So, but what we can change is the address. So let's change the address. I copy the address from the client information, Control C, and I place the address here, Control V. Okay, so the address is on there, and we will do that later. So this is kind of like page 1 and page 2. We'll insert that picture after. So let's save. And this is the end of lesson 2. We have gone through each one of these pages. Save, yes. So we have gone through each one of these drawing files. We've changed the customer information. We did the structural load calculation on the equipment plan. We did the electrical calculations on the single line diagram on the electrical plan. And we have changed all the customer information, made the data sheets correct, and we have created PDFs of each one of those data sheets. Everything that was 100% complete, we have created a PDF version of. So they are all down there, ready to be compressed. Now all that's left is Lesson 3 is going to be drafting the plan. Lesson 3 is going to be drafting the plan, and I will teach you how to draft the plan in options and copy and paste in site plan and layout. We'll talk to you then.